Now in this session we're going to look at flexural design and how to use Eurocode to determine the flexural capacity of an element. One thing to note is that we'll probably have to go back to first principles when applying what's in the code. So let's start by having a look at what Eurocode actually tells us. Now in the code it says the ultimate limit state moment resistance can be carried out making the following assumptions. So you can assume that plane sections remain plane, and that's a fairly standard approach. You may also assume strain compatibility between the reinforcement and the concrete. Again, that's a fairly standard approach. We can ignore the concrete tensile strength, and again that's fairly standard. And then we're told that we should use the stress strain limits given in section 3 of the code. We've already looked a little bit of section 3, but we're going to pull out the pertinent details in the next few slides. And to be honest, that's about it. That's all that Eurocode really tells us about flexural capacity. So we're going to have to work from the information given to get to some practical design guidance. So section 3 of Eurocode 2 actually gives us a number of stress-strain relationships that we can use for flexural design. The first one shown here is a parabolic relationship, and you can see once you reach a mean strength, then as the strain increases, the strength is reduced. Now this relationship is quite complex to use, so we won't be touching on it again in this session. The next relationship we're given is a parabola-rectangular relationship, and here we have a parabolic shape up until we reach our concrete design strength of FCD, and then for increasing strain we have constant stress. And again, this is quite complex to use, and the benefits are fairly small, so we're not going to be using this in this session. The next stress-strain relationship is bilinear, so we have a linear elastic shaped stress-strain relationship up to the concrete design strength, and then again we have for constant stress increasing strain. And again, while we're getting simpler, there's simpler methods that we're going to show you that you'll find easier to use in the first instance. So that brings us on to a rectangular stress distribution. So here we have just a rectangular stress block which is going to resist the compression, and this is probably a most familiar approach to most people, and we're going to use this to determine some design expressions. Now in what we're going to show you here, we're assuming that your concrete class will go up to a C50-60 and not beyond that. Once you go beyond a C50-60 concrete, you have to start reducing the maximum strain. You increase the value of the factor eta, and also you reduce lambda. So we're going to stick to the lower grades of concrete, which will cover the majority of most designs. So there is one further stress-strain relationship that I need to show you, and that is one for confined concrete. And by confined concrete we mean concrete that's always in compression. So it's in triaxial compression, and it's compression from all directions, and that actually gives you a greater capacity from the concrete, and you may use that in that situation. So the stress-strain relationship is shown there. It's something that's probably going to be used infrequently, but it's worth knowing that it's there for those situations. So let's take our concrete stress block, and we'll represent the center line of that compressive force with a force Fc, and that's matched by SST, which is the force in the steel. We can show the neutral axis, and the depth to that neutral axis is x. That's a dimension we will use from time to time. Now the depth of the stress block is lambda x, and the concrete strength should be taken as eta FCD. Now eta can be taken as 1 for the lower strengths of concrete which we're going to design for. So FCD equals 1.0 times FCK over 1.5. And 1.0 is the value for alpha CC. You may find in some countries it's taken as a lower value. Then FYD, the steel's design strength, is FYK over 1.15. We can now work out the force in the concrete, FC, and that's going to equal FCK over 1.5 times the breadth of our section, B, times lambda, which is 0.8, times X. And that can be simplified to 0.533 FCK BX.